Welcome back to my channel LinkedIn Farmer. Today's video is based on friction, chapter 9, class 8. Before starting this video, please like and subscribe to my channel LinkedIn Farmer. Let's start it. Introduction of friction. Friction is a fundamental force that opposes the relative motion or tendency of motion between two surfaces in contact. It arises due to microscopic irregularities on surfaces, which interlock and resist motion when they come into contact. This resistance to motion plays a crucial role in everyday life, influencing how objects move, the efficiency of machines, and even the way we walk and interact with our environment. Understanding friction is essential in various fields, from physics and engineering to materials science, as it shapes the behavior of objects and systems in diverse situations. Force of friction. The force of friction is the resistance encountered when two objects move or try to move against each other due to their contact. It arises because surfaces are not perfectly smooth at a microscopic level, causing irregularities to interact and hinder motion. Friction can be classified into two main types. 1. Static friction and 2. Kinetic friction. Static friction. This type of friction prevents an object from starting to move when a force is applied to it. For instance, consider pushing a heavy box across the floor. Initially, the box doesn't move because the force you apply is countered by the force of static friction between the box and the floor. Once you apply enough force to overcome the static friction, the box starts moving. Kinetic friction. Once an object is in motion, it experiences kinetic friction, which opposes its motion. An example would be a sled sliding on snow. As the sled moves, the friction between its runners and the snow slows it down. This is why you need to continue pushing or pulling the sled to maintain its motion against the resistance of kinetic friction. Other examples of friction include walking. Friction between the soles of your shoes and the ground prevents slipping while walking. The amount of friction affects how easy or difficult it is to walk on different surfaces. Braking in vehicles. Friction is crucial for braking in vehicles. When you apply the brakes in a car, the brake pads create friction against the rotors, converting the kinetic energy of the moving vehicle into heat energy and bringing it to a stop. Climbing. When you climb a ladder, the friction between your shoes and the rungs helps you ascend safely. Without sufficient friction, you might slip and fall. Writing with a pen. The friction between the pen's tip and the paper is what allows ink to be transferred onto the paper as you write. Using tools, whether it's turning a screwdriver, using a wrench, or opening a door handle, friction is essential for transferring force effectively and manipulating objects. Understanding the force of friction is vital for designing machinery, predicting the behavior of moving objects, and ensuring safety in various activities. It is a force that impacts our daily lives in countless ways. Factors affecting friction. Friction is influenced by several factors, which determine the strength of the opposing force between two surfaces in contact. These factors include surface texture. The roughness or smoothness of surfaces affects friction. Rough surfaces have more contact points and therefore higher friction compared to smooth surfaces. For instance, a rough road provides more friction for vehicle tires, while a smooth ice surface offers very little friction. Normal force. The force pressing the two surfaces together, known as the normal force, affects friction. Greater normal force typically leads to increased friction. For example, the weight of an object you are trying to move affects how much friction must be overcome. Type of surfaces. Different materials have varying coefficients of friction, which determine the strength of friction between them. Some materials have a higher coefficient of friction, leading to greater resistance, while others have lower coefficients, resulting in less resistance. Surface area. A larger surface area in contact can lead to higher friction. For example, shoes with a larger tread provide more friction on surfaces like wet pavement. Speed. In some cases, speed can affect friction. As the speed increases, the friction might increase due to factors like the buildup of heat at the contact points between surfaces. Temperature. Temperature can influence the state of materials and thus their frictional properties. For instance, ice becomes more slippery as it melts due to reduced friction. Lubrication. The presence of a lubricant, such as oil or grease, can significantly reduce friction between surfaces by creating a layer that separates them. This is commonly used in engines and machinery to minimize wear and increase efficiency. Pressure. Pressure at the contact points between surfaces can alter friction. High pressure can lead to deformation of the surfaces, affecting the frictional forces. Type of friction. Friction can be influenced by whether it's static, object at rest, or kinetic, object in motion, friction. Static friction is often higher than kinetic friction, meaning it might take more force to initiate motion than to keep an object moving. Air resistance. For objects moving through the air, air resistance can act as a form of friction, opposing the object's motion. Wear and tear. Over time, friction can cause wear on surfaces, changing their properties and potentially affecting the friction between them. Considering these factors is essential in various fields, from designing efficient machines and vehicles to understanding how objects move in different environments. Spring balance. A spring balance, also known as a spring scale or dynamometer, is a simple measuring instrument used to determine the weight or force exerted on an object. It operates based on Hooke's law, which states that the force needed to extend or compress a spring by a distance is proportional to that distance. The main components of a spring balance include a calibrated spring, a hook or attachment point to hang objects, and a scale with markings to read the measured force or weight. When an object is suspended from the hook, the spring stretches or compresses accordingly, and the scale indicates the force required to maintain the balance. Spring balances find applications in various fields. Weighing. Spring balances are commonly used for weighing objects in scenarios where precision isn't critical. They are often found in classrooms, kitchens, and markets for quick weight measurements. Educational tools. Spring balances are frequently used in science education to teach concepts related to force, weight, and the properties of springs. Tension and compression testing. They are used to measure the force required to stretch or compress materials, making them valuable in mechanical testing and material science. Field work. Spring balances are portable and easy to use, making them useful for field measurements where more sophisticated equipment might not be practical. Fisheries and agriculture. They are employed in fisheries to estimate the weight of caught fish and in agriculture for measuring produce, feed, or other materials. Force measurements. Spring balances are also used to demonstrate force in physics experiments and to measure force in simple mechanical systems. Spring balances come in various sizes and weight capacities, allowing them to be used for a wide range of applications. They provide a convenient way to measure force or weight in situations where high precision isn't required, making them a versatile tool in both educational and practical settings. Friction. A necessary evil. Friction, often regarded as a necessary evil, is an essential force that permeates our physical world, shaping our interactions with the environment and influencing the mechanics of countless processes. While it can impede motion and introduce wear, its presence is indispensable for stability, control, and the functionality of various systems. Friction's dual nature becomes evident when considering its disadvantages and advantages. On the downside, friction generates heat and wears down surfaces, leading to energy loss and mechanical degradation. In machinery and engines, it's the culprit behind inefficiency and the need for frequent maintenance. In everyday life, it can cause discomfort, hindrance, and even accidents. However, the seemingly adversarial force is also a crucial ally. Without friction, walking would be impossible, vehicles would skid uncontrollably, and gripping objects would be a challenge. Friction enables us to drive cars, write with pens, and engage in various activities that rely on traction and stability. It's a fundamental reason we can ascend stairs without slipping and manipulate tools with precision. In the industrial realm, controlled friction is harnessed to achieve specific outcomes. Brake systems utilize friction to bring vehicles to a halt, and clutches engage or disengage using friction to control power transmission. Moreover, innovations in lubrication and surface engineering aim to minimize the negative effects of friction, enhancing efficiency while mitigating wear. Friction's significance extends beyond mechanics. it's woven into the fabric of science and innovation. Researchers study it to design superior materials, improve efficiency in transportation, and uncover novel ways to optimize energy usage. Indeed, the pursuit of reducing friction has led to advancements in fields as diverse as nanotechnology in sustainable energy production. In essence, friction is a paradoxical force, one that challenges us as much as it empowers us. While its presence demands our attention and ingenuity to manage its undesirable consequences, it's also a vital ingredient that enables the intricate dance of motion, stability, and progress in our dynamic world. As we continue to explore its nuances, we uncover the delicate balance between embracing friction's essential role and striving to tame its less desirable effects. Increasing and reducing friction. Friction, the force that resists the motion between two surfaces in contact, can be both a friend and a foe. Depending on the situation, there are ways to either increase or reduce friction to achieve desired outcomes. Here's a look at strategies for manipulating friction. Increasing friction. Surface texture. Roughening surfaces can enhance friction. For example, tires designed with tread patterns provide better grip on roads, especially in wet or icy conditions. Pressure. Increasing the pressure between surfaces increases the contact points and friction. This is why pressing down harder on a piece of paper while writing increases the friction between the pen and paper, allowing smoother writing. Using coarse materials. Materials with higher coefficients of friction, like rubber or sandpaper, can be employed in situations where strong grip is needed, such as non-slip mats or shoe soles. Lubrication adjustment. In some cases, adding certain types of lubricants can actually increase friction. For example, sand can be used on icy roads to provide better traction. Interlocking mechanisms. Designing surfaces with interlocking mechanisms, such as the treads on tank treads or snow tires, increases the amount of contact between surfaces and thus enhances friction. Reducing friction. Smoothing surfaces. Polishing or smoothing surfaces reduces the number of contact points and lowers friction. This principle is used in bearings and axles of machinery. Lubrication. Applying lubricants, like oil or grease, between surfaces reduces friction by creating a barrier that separates them. This is common in engines, where lubrication reduces wear and energy loss due to friction. Ball bearings. In mechanisms like wheels, ball bearings are used to reduce friction by allowing the rolling motion to replace sliding motion. Aerodynamics. In vehicles, streamlining shapes are used to reduce air resistance, a form of friction, and improve efficiency. Low friction materials. Employing materials with low coefficients of friction, such as Teflon, in specific applications can reduce friction and wear. Teflon is used in non-stick cookware, for instance. Fluid dynamics. In fluid systems, like pipelines, using fluids with lower viscosity can reduce friction losses during flow. The ability to manipulate friction is essential in engineering, design, and various industries. By understanding how to control friction, engineers and innovators can create more efficient machines, enhance safety, and improve the overall functionality of countless applications. Wheels. Reducing friction. Wheels serve as one of the most ingenious solutions for reducing friction in various applications. By leveraging the principles of mechanics and physics, wheels significantly alleviate the resistance encountered when objects move against surfaces. This reduction in friction has profound implications across industries and everyday life. The magic of wheels lies in their ability to transform sliding friction into rolling friction. When a flat surface comes into direct contact with another surface, such as a box dragged across the ground, the friction opposing the motion is substantial. However, by placing wheels beneath the box, the interaction changes. The circular motion of the wheels enables the object to roll, minimizing the points of contact and thereby diminishing friction. From ancient carts to modern vehicles, wheels have revolutionized transportation. Cars, bicycles, and trains all rely on the principle of wheels to move efficiently with reduced friction. Moreover, the introduction of ball bearings further refines this concept. By incorporating small balls between the moving parts, friction is minimized, resulting in smoother motion and less wear. Beyond transportation, wheels are integral to machinery, manufacturing, and even leisure activities. Conveyor belts in factories, for instance, employ wheels to move items with less friction. Roller skates and skateboards capitalize on wheels to enable swift movement. Even office chairs utilize wheels for easy mobility. The concept of wheels extends its influence to various realms of physics and engineering. It showcases the power of ingenuity in transforming obstacles into opportunities. By harnessing the principles of rolling motion, wheels not only reduce friction but also exemplify how a simple invention can reshape the world around us, enhancing efficiency and revolutionizing the way we interact with our environment. Rolling friction and sliding friction. Friction, the force that opposes motion between surfaces, manifests in different forms depending on the nature of the contact. Two primary types of friction, rolling friction and sliding friction, play distinct roles in various scenarios. Rolling friction. Rolling friction occurs when an object rolls over a surface, like a wheel on a road. Unlike sliding friction, which involves two surfaces sliding against each other, rolling friction involves the interaction between a rolling object and the surface it contacts. The point of contact between the object and the surface changes as the object rolls, which significantly reduces the frictional force compared to sliding friction. Rolling friction is generally lower than sliding friction, making it more efficient for many mechanical systems. It's a fundamental principle behind the operation of vehicles, such as cars and bicycles. The wheels of these vehicles experience rolling friction, allowing them to move with less resistance and greater efficiency. Sliding friction. Sliding friction, also known as kinetic friction, occurs when two surfaces slide or move against each other. This type of friction is more prominent when surfaces are pressed together and their microscopic irregularities interlock, generating resistance to motion. Sliding friction is typically higher than rolling friction and requires more force to overcome. Sliding friction can be found in various everyday situations. For example, when you push a heavy box across the floor, the resistance you feel is due to sliding friction. The friction between your shoes and the ground when walking is also a form of sliding friction. In machines with sliding parts, like engines, proper lubrication is essential to reduce sliding friction and prevent excessive wear. Understanding the distinction between rolling friction and sliding friction is crucial for designing systems, optimizing efficiency, and minimizing wear and energy loss. Both types of friction have their place in the physical world, shaping the way objects move and interact in diverse ways. Fluid friction. Fluid friction, also referred to as viscous friction or drag, is a type of resistance encountered by objects moving through a fluid, such as air or water. Unlike solid surfaces, fluids are substances that flow and adapt to the shape of their containers. They can include both liquids and gases. As an object moves through a fluid, it experiences a force opposing its motion, which is known as drag. Fluid. A fluid is a substance that can flow and take the shape of its container. It includes both liquids, like water and oil, and gases, like air. Fluids exhibit the property of viscosity, which determines their resistance to flow. Viscosity is the measure of a fluid's internal friction, affecting how easily it can be deformed or moved. Drag. Drag is the force of resistance experienced by an object moving through a fluid. It opposes the object's motion and is caused by the interaction between the fluid and the object's surface. Drag force depends on various factors, including the speed of the object, the shape of the object, the density of the fluid, and the viscosity of the fluid. Fluid friction can be divided into two main types. 1. Laminar flow. In laminar flow, the fluid moves in smooth, parallel layers. This occurs at relatively low speeds and is characterized by minimal turbulence. Fluid friction in laminar flow is directly proportional to the viscosity of the fluid, the speed of the object, and the size of the object's cross-sectional area. 2. Turbulent flow. Turbulent flow involves irregular, chaotic movement of the fluid particles. This type of flow occurs at higher speeds and is characterized by eddies, swirls, and sudden changes in velocity. Fluid friction in turbulent flow is more complex and can depend on various factors, including the roughness of the object's surface and the Reynolds number, a dimensionless parameter that describes the ratio of inertial forces to viscous forces. Fluid friction has significant implications across a range of applications. Aerodynamics, in aviation and the design of vehicles. Understanding fluid friction is crucial. Streamlining shapes are used to minimize air resistance, enabling more efficient movement through the air. Hydrodynamics, fluid friction influences the design of ships and submarines, affecting their efficiency and maneuverability in water. Pipelines and fluid transport, fluid friction affects the efficiency of transporting liquids and gases through pipes. Engineers must consider the effects of friction on pressure loss and energy consumption. Sports and recreation, fluid friction comes into play in activities like swimming, where reducing drag is essential for optimal performance. Weather and atmospheric phenomena, understanding fluid friction is vital for predicting weather patterns and atmospheric behaviors, as it affects the movement of air masses and the formation of clouds. In essence, fluid friction plays a significant role in shaping how objects move through and interact with fluids. Its effects are present in both natural and engineered systems, influencing everything from transportation to sports and scientific research. Thank you for watching. Please like, share and subscribe.